All the sorting algorithms we have exposed so far are comparison-based sorting algorithms. They sort data by comparing items. But we have a bunch of other sorting algorithms that don't use comparisons. They use basic math. Counting sort is the simplest of these, and we're going to talk about it in this video. So let's say we have a list of integers in the range 0 to k. This assumption is very important, as you will see shortly. Here we have an array of 7 integers, and k, or the maximum value, is 5. To sort this array, we need to figure out how many times each item appears in this array. In other words, we want to know how many 5s or 3s or 2s we have. We can represent the counts or frequencies using another array. So we iterate over our input array. The first item is 5. Now we go to index 5 of the counts array and increment the value by 1. That means so far we have found 1 5 in our input array. As we read more items, we'll update these counts, okay? So let's read the next number in our input array. That's 3. Again, we go to index 3 of the counts array and increment the value by 1. Next, we read 2 and update the count. The next number is 5 again, so we update the counts array accordingly. Next, we have a 4. So we update the counts array. We have another 4. And finally, we have one more 5. So we set the count to 3. Our counts array is ready. Now we can use it to sort the data and refill the input array. So we iterate over the counts array. We don't have any zeros or ones, but we have 1, 2. So the first item in our input array should be 2. Let's keep going. We have 1, 3. So the second item in our input array should be 3. We read another item in our counts array. That's telling us that we have 2 4s. So the next 2 items in our input array should be 4s. Let's read the last item in the counts array. It says that we have 3 5s. So the next 3 items should be 5s. Look, our array is sorted. This is counting sort. Instead of using comparisons, we count the occurrences of items in the input array and use that to sort the data. Now let's talk about the time and space complexity of counting sort. Space complexity is pretty straightforward. We need to allocate extra space for the counts array. The size of this array is dependent on the maximum value in the input array. If k is the maximum value in our input array, counting sort requires O of k space. What about time complexity? Well, first we need to populate the counts array. Doing so requires iterating over the input array. This is an O of n operation. Then we need to iterate over the counts array and refill the input array. This is an O of k operation. So the time complexity is O of n plus k, which we can simplify to O of n. So it's linear. Here on BigOCheatSheet.com, you can see that an algorithm with linear time complexity is much faster than an algorithm with time complexity of n log n. So counting sort is much faster than the previous algorithms in this section. But this speed comes at a cost, the cost of allocating extra memory. This is what we call time-memory trade-off in computer science. There are a lot of situations where we can make a program or an algorithm run faster, but at the cost of extra memory. So we have to do a trade-off between the execution time and memory. So we should use counting sort when allocating the extra space is not an issue. Also, as I told you earlier, all the values should be positive integers. Otherwise, we cannot use them as indexes of the count array. And it's best if most of the values in the range are present in the input array. Otherwise, we'll end up with a lot of empty or 0 elements in the counts array. For example, if we replace one of the 5s with, let's say, 1 million, our counts array would have 1 million items and most of these would be 0. That would waste a lot of space. So counting sort is suitable for scenarios where most of the values in the range are present. All right, enough theory. Now we'll spend 20 minutes on implement this algorithm, then come back see my solution.